are attending the meeting. So let me show just to have a. Okay, so good morning, everybody, and in the name of the organizing committee, I give a warm welcome to all the speakers and participants, and also thank you all for the interest of the meeting. Wishing that everybody is in good health, it seems for the audience. We now start this meeting, Topological Quantum Matter Foundation Applications, which will take place during the remaining of the week according to the schedule that is published in the website. Okay, there you can find the titles and the abstracts of the talks. And let me just mention that the meeting is hosted by the Universidad Nacional Autónoma de México. You can see here, and is organized by a collaboration between colleagues from the Institute of Nuclear Science, Instituto de Ciencias Nucleares, and the Faculty of Chemistry, la Facultad de Química de la UNAM. Okay. Just to have an idea of our intentions with the meeting, let me recall that recent developments in topological quantum matter increasingly emphasize the enormous possibility of a fruitful collaboration among areas like condensed matter physics, high energy physics, mathematics, maybe mostly in the area of topology. So this has been precisely our motivation for the choice of topics in this event, which we expect to be reflected in the presentation, okay? On the other hand, this means that the speakers and the audience come from very different areas of expertise. And one of the goals of the meeting is to establish some communication among these areas. So in this sense, we have asked the speaker for their help in this matter in order to make an effort such that the talks are not only addressed to experts in the subject, but can reach a broad audience. Okay, so let me just mention for the students or people who's not very involved in this area, that the study of topological matter present at least two main directions, okay? On one hand, it is of natural interest in condensed matter physics, where the aim is to establish theories to explain their properties, and also to develop experimental applications which might lead to technological progress involving new material. On the other hand, topological matter provides an excellent opportunity to test and even extend many concepts and ideas in high energy physics, such as, for example, anomalies, gravitational theories, violation of space-time symmetries, topological field theories, the search of Majorana fermions, just to name a few. In other words, many very constrained or dangerous realization in high energy physics might become perfectly physical in condensed matter. Okay? Roughly speaking, then, the bridge that provides this connection is the low energy behavior of the tight binding Hamiltonians describing such materials, which yield Weyl or Dirac-like Hamiltonians that can be studied using the standard particle interpretation and method of high energy quantum field theory. Okay. Finally, I would like to mention that there's a little bit of propaganda, that in the web page we have posted a postdoc announcement for recently graduated students who might be interested in working here in Mexico City in some of the topics to be covered on the meeting. Well, thank you very much for this time. And now without further delay, I present the first speaker of the meeting, which is Professor Landsteiner, Karl Landsteiner, from Universidad Autónoma de Madrid, who will talk about quantum anomalies in matter. So please, Professor Landsteiner.
Okay, okay, thank you very much for the invitation to this very interesting workshop and for the introduction. Yeah, So the title of my talk is Quantum Anomalies in Matter, and I hope that I will be able to explain more precisely what I mean by this. The talk is based on the mostly, of course, some original research, but which is summarized here in this series of 3 reviews, which I've also co-authored. The most recent one last year with Maria, who is also in the, I'm afraid I have to go now to the, and open the door. I'm sorry for that. Just, oops, I'm sorry for that. Since there was children coming back from school and without the key, or the key didn't work. I'm sorry. Okay, let me go back to physics. Okay. So here's the outline of my talk. I will first define what, say, from the high energy perspective, quantum field theoretical perspective, we call an anomaly. Then I will introduce John Simon's theories as effective actions for anomalies. I will discuss the anomalous Hall effect and what is called the Chiral Magnetic and Chiral Vortical effects. I will point out from my perspective what relation this might have with the physics of black holes, something which I think in high energy we learn from this ADS-CFT correspondence, which comes from string theory. And then something more back to Earth. I will try to apply these formulas for this anomaly-induced transport phenomena to some real-world materials, so-called Weyl semimetals, and will derive some formulas which apply to Weyl semimetals to transport properties of Weyl semimetals in magnetic fields. Okay, so quantum anomalies sound a bit scary, and indeed, if you just Google for quantum anomalies, you find something like this, which are very scattered pictures. But these popular views are sometimes quite inaccurate. And the good news is you can actually survive quantum anomalies. So there's this series of comics by Brazilian author Leo, which are very interesting and funny. The 4th series here is called Quantum Anomalies, and the survivors of the quantum anomalies. Let's see if we can survive them. Okay, so now, what's an anomaly? Now, in high energy physics, when I was back in grad school, we learned that an anomaly is a non-trivial element of the BRST cohomology. It goes number 1 on the space of integrated local monomials in the fields. Okay, that's a very complicated mathematical definition. So what it means is the following. You have your path integral over the fermions, and this might be chiral fermions. You couple them to some external gauge field. And in most of my talk, you should think of these gauge fields not being dynamical by themselves, coupled, having dynamics described by a Maxwell equation or anything like this, but you should think of them just as a classical source for the operator, which is the corresponding conserved current. So if I would, if you can do this path integral, then you can generate an effective action. And this effective action, if you functionally differentiate with respect to this gauge field A, you could generate correlation functions of currents, conserved currents. And the anomaly appears when you study the gauge invariance. Classically, of course, the action is gauge invariant because the current is conserved. But quantum mechanically, if you study, and I've introduced here what is called the BRST operator, which is sort of, just think of it as being the gauge transformation. And quantum mechanically, it can happen that this quantum functional effective action, which I've constructed, is not invariant under the gauge transformation. Now, there's a small or important caveat to that. It might be that you can modify this effective action by adding some local term to it, a local counter term, such that the anomaly vanishes. So if the anomaly by itself would be given by the gauge variation of a local effective action, then it wouldn't be really an anomaly. You could reabsorb, redefine the effective action and get an anomaly-free quantum theory. So that is what is meant in high energy physics by the anomaly. And of course, these local counterterms, they depend on sometimes how you regularize the theory. You know, in quantum field theories, in some sense, it's not complete. You always have to specify a specific regulator. The form of these counterterms might depend on the regulator, but you know that every regulator you choose differs by another regulator by at most some local counterterms. So in this sense, this is a universal phenomenon. Okay. Now here, the typical form, so for a single chiral fermion, the anomaly would take this form. So C is the gauge parameter, and F wedge F. So I'm using form language, but just think of it as being F mu F rho lambda contracted with an epsilon tensor, epsilon mu lambda rho, and F mu F rho lambda. Or just the inner product of electric and magnetic field. That's basically what it is. And so that's the form of the anomaly. And famously, there's no way of writing this as the gauge variation of a local effective action. You can write it as the gauge variation of a non-local term, like this, which has been pointed out somewhere in the 80s. However, it is also possible to write the anomaly as a gauge variation of a local term, but you have to employ a trick. You have to modify the dimension of spacetime. So originally, this would be for a 4-dimensional spacetime. But if you allow yourself formally to go to 5 dimensions, then you can actually integrate the anomaly into a local effective action. And this local effective action is the Chern-Simons term. It takes this form of AFF. And famously, there is, of course, an application in condensed matter physics of this, a very well known, which is the quantum Hall effect, or say, in high energy physics, we would call this anomaly inflow, or it's also known as the Chern insulator, where you have some band in an insulator, but the electron wave function as it is varies over the Brillouin zone, has some non-trivial topological properties, which is measured by the first Chern number of Berry curvature, which I'm not going to. This comes for sure later in some other talks. But from the quantum field theory perspective, what I have is basically the UV theory would be some massive 2+1 dimensional Dirac fermion, which I integrate out, and then I generate at low energies this Chern-Simons term. This is in 3+1 dimensions. But then famously, there's this bulk edge correspondence, bulk boundary correspondence for topological matter, and which tells me that on the boundary of such a material with a non-trivial Chern number in the Brillouin zone, on the boundary, there must live necessarily some ungapped state. And in this case, for a Chern insulator or in the quantum Hall effect, it's a chiral fermion, which lives here on the boundary. And so to give the full description of this system, you would have to include not only the full low energy description of the system, not only the Chern-Simons term in the bulk of the material, but on the boundary, you also would have to supplement it by the effective action, which comes by integrating over these massless fermions, chiral fermions. And of course, these guys have an anomaly. But then the anomaly which appears here on the boundary is cancelled by the non-invariance of the Chern-Simons term in the presence of a boundary, because you can easily see if you do a gauge variation, you get here a total derivative and you get only contributions on the boundary. And the coefficients of this Chern-Simons term is chosen precisely such, or it appears precisely such, as to cancel the anomaly which appears here on the edge states. But not only are there edge states, they are also populated. So there are really massless states living there, whereas here in the vacuum, here we have a vacuum, it's topologically non-trivial, but there are no local degrees of freedom. On the boundary, there are local massless degrees of freedom. And so they can be described by a chemical potential. So there's a left and a right chemical potential. In equilibrium, you would say both are equal, and so there is no net current flowing, net current flowing here. But if you would increase, for example, the chemical potential of the fermions you inject fermions here on the right edge, you would get more fermions, electrons moving upwards than downwards, and you would get a net current, which is sort of the boundary description of the Hall effect. Okay, and all of this physics is basically dominated and determined by the chiral anomaly. But what I want to point out that there are two phenomena here of currents. One is a bulk current, which is sort of coming from the Chern-Simons action. If you vary the Chern-Simons action with respect to the gauge field, you formally also get the expression for the current. And this current is just given by this expression. And it lives in the bulk of the material. So it's an electric current. Even if there are no charged at the Fermi surface, you put the Fermi surface in the gap of the material, and there are no charged particles there, but there's still a current. So this is an effect of this topological property of the vacuum, so to speak. But on the edge current, you really have matter there. You have these chiral fermions, and these chiral fermions, they also produce a current. And the current is just given by the chemical potential. But both of these currents, because of this anomaly inflow argument, and that these anomalies have to cancel, both of these currents are proportional to the anomaly coefficient C. And in this particular simple system, C would also tell you the number of edge modes. So for example, in the simplest case, you just have one edge mode, then C has a specific number, 1/4 pi squared. And so this is very well understood, how this works in the vacuum, because you just have this Chern-Simons action, and you differentiate with respect to the gauge field, and you get a bulk term. What is a little bit more interesting to study, and this will be the thrust of my talk, is how does this current from the gapless topological matter comes from. This is a current which, if you don't change dimension, it is described, also determined by the anomaly, but it's in this case 1 + 1 dimensional, or in the case which is most interesting to me, 3 + 1 dimensional, so 3 space + 1 time dimensional current induced by an anomaly and of gapless matter, so massless fermions. Okay, so what we have established already is that, and that's for me the key observation, that the effective action of this fermion system of chiral fermions, if I integrate over the fermions and just keep the gauge fields, this has an anomaly, but the anomaly is exactly equivalent to the anomaly I get when I go to one higher dimension and study the Chern-Simons action in one more dimensions. So from the point of view of anomalies, they are completely equivalent. They produce exactly the same anomaly. And so the question is, can I derive these currents, which come from the topological matter, also by a Chern-Simons action? And the answer is yes. And it actually came from methods from string theory, from the ADS-CFT correspondence. And the way it works is as follows. So here I do this immediately for the most complicated case, so to speak. I will study the so-called gravitational anomaly in 3 + 1 dimensions. So that's an anomaly which is proportional to the Riemann curvature, trace R, wedge R. And you can form a Chern-Simons term, just usually the Chern-Simons term, so curvature times gauge field. Right, so this gauge field here, it's best to think of this gauge field to be a gauge field which, yeah, is there a question? Okay, then I go on. It's best to think of this gauge field as the gauge field which couples, for example, to the axial current. So the current which measures the number of left-handed fermions minus right-handed fermions. Okay, and so I know that I produce the anomaly on the boundary of a 5-dimensional manifold if I just vary with respect to the gauge field. But what is this manifold? And I said already before, in the massless case, it's not enough just to say, okay, this is a manifold and there's vacuum, there's nothing more. because there's also matter, and matter can be in specific states. And the state, especially near equilibrium or at equilibrium, the parameters with which you describe the state are the chemical potential and the temperature. So what you have to do now is to encode the information that this system is at finite temperature in this 5-dimensional manifold. So it's a 5-dimensional space, which is not a physical space, but it's a mathematical invention, which I modify in such a way, or which I choose in such a way, such that it contains the information that the system is at finite temperature. And here comes in what we have learned about studying black hole physics. We know precisely what is a 5-dimensional, a space which encodes temperature. Since Hawking in the 70s told us that a black hole is actually a black body and it radiates at the Hawking temperature, we know how to encode temperature into geometry. And this is what I'm doing here. So what I'm saying is, well, I take the geometry of this 5-dimensional space to be a 5-dimensional black hole. Then I know that on the boundary, this thing is completely equivalent to the theory living on at finite temperature. And a generic, and what I'm also doing here, because I'm interested in this chiral vortical effect, is I choose a background which is a slowly rotating black hole. So I want to know how the system reacts when it is slowly rotating and at finite temperature. And it has this form of anomaly. This is what I'm asking. And this is the general form of such a metric. G and F are completely arbitrary functions. The only thing I want that this is a regular geometry that tells me, for example, that G should nowhere in the interior. So R is the coordinate which parameterizes this 5th dimension. That demanding that this should be a regular geometry, it means that this G of R should never go to 0 somewhere in the interior. On the boundary, F and G, I take just to be 1. Then I just get on the boundary the flat space. This identify with the space we are really living in, the 3+1-dimensional space. And F, there is an interesting topological abstraction on F. So F has to be such that on the horizon of the black hole, the derivative, F has to vanish. That's the definition of what is the horizon. And its derivative has to be proportional to the temperature. So Hawking did it the other way around. Hawking said, well, you know, F vanishes on the horizon. And then if I look from far away to the black hole, it looks to me that there's a flux of particles at the finite temperature coming to me, and the temperature is determined by the derivative of this function F at the horizon. Now, knowing this, I turn it around. I say, I know I want this geometry to represent temperature, so I take T, and then I ask, what is the property of the geometry, which is the derivative of F? Okay, and then there's some further, more fine-tuned condition, which I don't want to go into. And that's all that you need to know. You don't need to know anything more in order to compute what is the current which comes from this effective action. And the current I calculate by varying this effective Chern-Simons action with respect to the gauge field. And the gauge field I just take to be a constant gauge field outside this horizon. And then you pick up an integral. Bg is the rotation parameter. So Bg is what is called the gravitomagnetic field, but just think of it as the angular velocity. It's actually twice the angular velocity of this black hole with which it rotates. And then I evaluate just this R term, and that's it. In this geometry, which represents the theory at finite temperature, slowly rotating, that's what I pick up. Not so surprisingly, this is a topological term, and I pick up a total derivative. And it's completely determined by these boundary conditions. And the boundary condition which plays a role is the one at the horizon, and only F prime plays a role. Everything else vanishes from this integral, everything else is 0, and only this term, which is determined by saying that it has to have the temperature T, only this term contributes. And like this, I can compute the current of a theory which has this form of anomaly at finite temperature if there is a small rotation parameter, if there is a small angular velocity. And it's given by this current. And this is called the chiral vortical effect. So the claim is that this is completely universal. Whenever a theory has this form of anomaly, and you put it at finite temperature and you spin it a little bit, then it generates a current along the axis of rotation, and the current is proportional to this anomaly coefficient, and it's quadratic in the temperature. And that follows only from these topological properties of the geometry and of the fact that the anomaly is represented by the Chern-Simons term. Okay. Okay, and this is, of course, the famous black hole picture. So, and you can do the same for the same philosophy works also for the other sort of phenomena, like the so-called chiral magnetic effect. So in this case, the relevant anomaly is the usual axial anomaly, which is here again. A is the axial gauge field, so the gauge field which couples to the axial current. And V is the usual vectorial gauge field, which couples to the usual, say, electric current. And that's the relevant Chern-Simons term. And again, in this 5-dimensional space, I don't take this as a real space. I take this only as the space which encodes that the system is in a specific state. And at this time, this is insensitive to temperature. Temperature is already related to properties of the metric in this picture. But what I can encode here is the chemical potential. And the chemical potential is encoded in properties of this gauge field. In particular, if the theory has some form of chiral imbalance, meaning that there are more left-handed fermions than right-handed fermions, I can parameterize this by a so-called axial chemical potential. And the axial chemical potential is basically given by the background value of the axial gauge field, of the temporal component of the axial gauge field. And then if I go through the same steps, again, now I know already that the geometry is basically a black hole, but it's not really relevant here because it doesn't see any of the geometry. It just sees the topology of this black hole, which knows that it has a horizon and it has a boundary. That's all I need to know. Bianchi identity tells me, for example, that if there's a magnetic field, it's completely independent of the 5th dimension, so I can switch on this magnetic field. And I can vary with respect to the vectorial gauge field to calculate, say, the electric current or the vector-like number current, particle current. And I get 2 contributions. That's slightly different here from the previous example. I get one contribution, which is just the bulk, which, as before, which I have to integrate on this sort of black hole geometry, and one contribution, which is a pure boundary contribution. And if I take both into account, yeah, I get this. And C is, again, the anomaly coefficient, which in this case, say, for a chiral fermion, I guess, or for the Dirac fermion here, it would be 1/4 pi squared. It's important that there are these 2 contributions. Okay, and I will come back to that. And you can, with the same effective action, because it depends on 2 gauge fields, it depends on the gauge field which couples to the axial current and on the gauge field which couples to the usual vector-like current of particle current or electric current. I can also calculate how much axial current I would get by the same means. But because of the particular structure of the Chern-Simons term here, I only get this term, a bulk term. And here the answer is therefore slightly different. I just get this contribution from the bulk, which I call mu. But the coefficient is the same because it comes from the same anomaly. It's just the boundary terms are different. And this is what is called in high energy physics, the chiral separation effect. So with this sort of method, calculations are probably look a bit complicated, but once you get used to this language of differential forms and study a bit black hole geometries, and so the calculations are not very complicated. And with this philosophy, you can calculate all these currents, and all of them depend on the effect that there is an anomaly, and say that you are in a situation which is easily describable by chemical potential and temperature. Okay, and so this is the full picture. So this is a bit it's a complicated formula, and I've just noticed I've compiled these formulas with wrong graphics. That's a bit flaky. Okay, this is the general form of anomaly. So the first term of these anomalies, they tell you that the current is not conserved in the background of gauge fields. And what the indices A, B, C are, they are different symmetries. So for example, a chiral, for a Dirac fermion, right? For a Dirac fermion, I can count the number of right-handed fermions plus the number of left-handed fermions, or I can count the number of right-handed fermions minus the number of left-handed fermions. So there are two currents which are vector-like and axial currents. So you could think of these indices AB being like vector and axial. And of course, the theory can be more complicated. There can be more, more fermions, more symmetries, axial symmetries, vector-like symmetries, and so on. And this is the general formula for this general theory with general symmetries. And this is the so-called gravitational contribution to the axial anomaly. Now, one thing which is important here is to keep in mind that for me, the gauge fields and even the metric, they are not dynamical fields. So there is no real curvature here. Everything, what I'm saying is that I need a field, a classical field, which couples to the energy momentum tensor. So everything I want to talk about is the energy momentum tensor. And in order to do this in a covariant way in quantum field theory, I formally couple the system to a metric and make it covariant under general coordinate transformations. Then I have a way of speaking about correlation functions involving the energy momentum tensor in a covariant way. And this is the meaning of this term. So it doesn't mean that this anomaly is only there if the theory is on a curved space. The anomaly is always there, but it appears in different correlation functions. What the metric here means is it's not dynamic, it's just the source for insertions of the energy momentum tensor, of this operator, quantum operator, energy momentum tensor. And what this equation tells you is that for these chiral fermions, the anomalies tell you that it's not possible, even if classically all these currents and the energy momentum tensor are all conserved, quantum mechanically, it's not possible to keep all these conservation laws. You necessarily have to sacrifice a subset of the conservation laws. And this is what, even in flat space, so even in flat space, even without any background electric and magnetic fields or whatever, some of the correlation functions involving the divergence of the currents or the divergence of the energy momentum tensor, some of them will not be zero. And this is the meaning of this equation. So the anomaly is really there, is a property of the theory, even in flat space, and even in the absence of external gauge fields. The way it's measured theoretically in quantum field theory, which tells you that you have an anomaly, are these so-called anomaly coefficients. They're very easy to calculate. You divide your fermions up into left-handed and right-handed fermions, and then you pick a symmetry, like the axial symmetry, and you look how this right-handed fermion, what's the charge of this right-handed fermion under symmetry number A. Then you multiply, then you build this triple product of charges, right? Symmetry number A, symmetry number B, symmetry number C of the same fermion, and you sum over all the right-handed fermions over this triple product minus over this triple product of the left-handed fermions. And if this sum is not zero, then there is an anomaly. And for the same way, for the energy momentum tensor or for this gravitational contribution, there's a similar anomaly coefficient, and it's this one. It's even simpler. You just sum over the charges of the right-handed fermions minus the left-handed fermions. And that tells you when you have to be careful with your definition of energy momentum tensor, because it might not be conserved, or some current might not be conserved when you compute correlation functions with the energy momentum tensor. Now, with these arguments from these anomalies, the transcendent, and there are many other arguments or explicit calculations in this series, what transpires is that when this happens, then you generate this at finite chemical potential and finite temperature in a theory containing such chiral fermions, you generate these currents. And so proportional to the anomaly coefficients. So this is the generalized form of the chiral magnetic effect, where I imagine now I have a magnetic field, but this is not the usual magnetic field. It's a magnetic field in this invented gauge field, number C. For example, the axial gauge field, right? The axial gauge field, which couples to the axial current. I imagine I switch on some magnetic field in this fiducial gauge field, and then, and if then there's a chemical potential For the symmetry number B, for example, axial chemical potential will tell you you have more left-handed than right-handed, or more right-handed than left-handed fermions. If this comes together, then you generate a current for the symmetry number C, A. So that's the meaning of this formula. And then for rotation, if you rotate, there is a similar formula, which is called the Chiral Vortical Effect. And again, it depends here on the chemical potentials, and it's related to this first type of anomaly. And there's a temperature part, which is this T-squared term, and that's related to this kind of anomaly. So the interesting thing here for the quantum field theorists, when we first saw these formulas, when we derived them, what is very unusual here is that we don't need to be in curved space in order to see any effect, say, of this. We don't need to switch on F to see the gauge fields, right? It just with rotation is fine. Rotation, chemical potential, and temperature. And the anomalies have an effect to generate these currents. And this is why I call this anomalies in matter. So instead of applying electric magnetic fields, putting the theory in complicated geometries, I can substitute this by driving the system into a specific state, which is chemical potential, describe the chemical potential and temperature, and I see effects which are there if and only if these anomaly coefficients are not zero. So in this sense, anomalies can be measured in matter. Okay, so this is, I'm sort of half through, yeah, a bit more. Okay, I've gone through all of this, but it's just a summary. There's, of course, many more. There's a role for more complicated anomalies, global form of anomalies, and so on. For condensed matter applications, I think there is a challenge which we have not yet properly addressed. Of course, in the simple systems, we always map this to Lorentz invariant system, and then we can apply everything which is known about the systems from quantum field theory studies, which always have underlying Lorentz symmetry. Condensed matter system, only a subset of systems like Weyl systems are, in the same universality class or describable by Lorentzian, effective Lorentzian theories. But there are many non-Lorentz invariant systems. They have also interesting phenomena like Hall viscosity. And so there's a question, can we also describe this in quantum field theory language with anomalies and so that? There are some partial answers, but it's not yet fully studied. Okay. Now, this is lots of theory so far. The question is this theory useful for anything? Or is this just a theory? And so my next claim is it's actually useful for something. Okay. And of course, what I want to study is this so-called class of materials, which are called Weyl semimetals. And now, all of you, most of you understand this picture, these graphics here. I have very vague ideas of what this means. What I understand is that for me, the important region is this little window here, but there are some crossings, band crossings, and I simplify this extremely further. I just think there's in the vicinity of the band crossing, this upper and lower band, they look like this, and the Fermi surface is somewhere near this band crossings. And then I know from a paper back in the 80s by Nielsen and Ninomiya that famously these band crossings are such that they always come in pairs, that one of these band crossings effectively is described by a chiral fermion in 3+1 dimensions with left-handed chirality, whereas the other one necessarily has to be a chiral fermion of right-handed chirality. And so basically this is like a Dirac fermion. And now I know all the theory of Dirac anomalies and Dirac fermions and so I can just apply it to this Weyl semimetal. But of course, I have to map all the parameters to my Weyl semimetal theory. And one way to do this, here's another cartoon. I have to understand what are all the parameters, right? And so these left and right-handed fermions, they don't live at the same point in momentum space as they do in high-energy physics, but they are separated in momentum space. And the separation is conveniently, so since it's chiral, left and right are at different points, It's conveniently described by actually a background value for this axial gauge field, which I introduced before. Then also the crossing points might not be at the same energy, they might also be shifted. Again, I can describe this with a temporal component of an axial gauge field. And then what in high energy physics we call the chemical potential is actually, say, if this is the Fermi surface, the chemical potential would be this distance here. So how far the states are filled above or below the band crossing point. And for the right-handed fermions is this. If you put everything together, and then you live in a Brillouin zone, which is a compact space. In high energy, we have non-compact momentum, but we have to introduce a cutoff. And so I have to regularize this theory with a cutoff, and the cutoff must be such that it's in the same, that it has the same topological properties as the Brillouin zone, which in particular means it has to be a gauge invariant cutoff, which is anyway what we always do in high energy physics. So if you do that, you can calculate these anomalies, and you find, for example, by these formulas I showed before, this formula for the Chiral magnetic effect. And if you are precisely in equilibrium, then these both contributions, which I talked before, they are precisely equal and they cancel. And in the beginning of this Chiral magnetic effect, many people forgot about the second term. They didn't write it down, or was not so clear. And then it had this strange property that apparently there was a current in equilibrium, but there are very old arguments back from the 20s and 30s which tell you that that can never happen. Current cannot, at least the gauge current, an exactly conserved current, cannot be different from zero. In equilibrium, it must always be out of equilibrium. And so this was a little bit confusing in the beginning, but with a proper quantum field theory treatment, with the proper regulator, and so you get the right result that precisely in equilibrium, it does vanish. Of course, eventually you want to go to a situation where you're slightly out of equilibrium. And what you can modify is the occupation numbers. You can try to pump a little bit chirality into the system, say, put a little bit more right-handed and left-handed fermions. And how to do this, and then this formula would not be, these two terms would not be exactly compensated, and then you would get an effect. Okay, and also this separation here, this has an effect. This gives a bulk Hall current. But okay. So how can we induce this chiral imbalance in order to go away from this equilibrium situation where we just don't have an electric current? Now, the key observation here is that there's a hierarchy of timescales, scattering timescales in this material. So the first thing these electrons do always they scatter on. So this is very naive now. Be warned, because I'm not the condensed matter physicist. So I have a very naive picture about what electrons do in a crystal. But here, my picture is that they first hit some impurity, and then they get scattered. And this is elastic scattering. And what it does, it relaxes momentum. So when an electron hits some, it gets scattered in a random direction, and it loses its directed momentum. And on average, momentum just averages out to zero. So this is the kinetic relaxation time. This is the fastest relaxation in the system. And so that means I don't have to care about momentum. Momentum is relaxed to zero. It's not really a conserved charge in the system. The next thing is intervalley scattering. So sometimes these electrons scatter very hard on an impurity, so hard that they actually can scatter over a large region in the Brillouin zone, large region in momentum space, and effectively end up in the other Weyl cone. From a high energy perspective, that would mean they change chirality, right? So this I model as a chirality changing transition. And then what I suppose is happening much, much later on a time scale much larger than any of these scattering events is electron-electron interaction. If this is not true, then you would have some hydrodynamic system, but this is very, very rare in condensed matter. And then I can set up an effective theory which takes care of the particle transport, quasi-particle transport, where I only monitor the quasi-particle number and the energy in each Weyl cone. So I set up a conservation equation for each Weyl cone. It's not completely conserved because the particles can scatter out of one Weyl cone into another due to this intervalley scattering. And this is given here by this 1 over tau, which is this intervalley scattering. I don't need to take care of momentum because I assume momentum is relaxed much earlier than any of this. So these are my long-lived variables. Particle number for each Weyl cone and energy in each Weyl cone. And then I apply magnetic field and measure how much, I apply a magnetic field. And on one end, I inject electrons, or I apply an electric field or a voltage. Or I can also increase the temperature a little bit on one end of this Weyl material. So this is my driving force, a gradient in chemical potential, or a voltage, or a temperature gradient. And then I use these expressions of these anomaly-induced currents and the conservation or non-conservation equations and blah, blah, blah. And I can calculate effective how much current is generated in this situation where you have a temperature gradient and a chemical potential gradient or an electric field. And I can encode this in a conductivity matrix, and this conductivity matrix is all proportional to this anomaly coefficients, right? So here, this term, for example, that comes from the chiral magnetic effect, which is induced by the usual chiral anomaly. This term comes from this gravitational contribution to the axial anomaly, and it's activated by this temperature gradient. And massaging this in a standard way, you can compute this conductivity matrix. And okay, and so for example, if the magnetic field is very small, then I can assume that the free energy is just the free energy of chiral fermions, which is given by this equation in a chemical, depending on chemical potential and temperature. Plug this into these expressions, which I get from the anomaly-induced transport, with all these anomaly coefficients, which you have seen, 1 over 4 pi squared, 1 over 192 pi squared, and whatever. And I get contributions to the electric conductivity due to the anomalies, to the thermoelectric conductivity. So how much electric current do I get due to the temperature gradient, and thermal conductivity? How much thermal current, heat current do I get due to the temperature current? And there are some checks I can do on this. For example, if I go to high chemical potential, I can compute this Lorentz ratio. And everything I've used to derive this is basically the anomaly coefficients. Here I've plugged in anomaly coefficients for chiral fermions. But if I go to the situation where the chemical potential is very large and the temperature is small, I can expand these complicated formulas at small temperatures, and this is what I get. And that is a ratio of anomaly coefficients from a high energy perspective. But of course, from the condensed matter perspective, this is a very well-known basic law of condensed matter physics, the Wiedemann-Franz law. Right? This is the Lorentz ratio, and this pi squared kp squared, I've reinstituted the Boltzmann constant here, over 3e squared is measured by Wiedemann-Franz and Lorentz somewhere in the 19th century. And that comes up as a ratio of coefficients of like anomaly coefficients for the usual anomaly and this gravitational part of the anomaly. And also you find the Seebeck formula from this. And so all these things work very nicely. On the other hand, what is very easy also is to go to extreme quantum limit. You assume all the particles are in the lowest lambda level, then the effective, the free energy for the theories become very simple, and then you get very simple expressions for these conductivities, and again, you get Wiedemann-Franz law, which in this case, in the ultra quantum limit, it's actually exact. So you don't have to go to large chemical potential or anything like that. And I think this is also a very well-known fact for one-dimensional fermions, like quantum wires or something like that. So basically, in the large magnetic field, you have the theory reduces down to a 1 + 1 dimensional theory, because the electrons can only move along the magnetic field lines. And in between, you have to sum over lambda levels, of course, and this has been done here. At least I know 2 groups who have done that. Okay. And how does this play out in experiments? So this says that if you switch on a magnetic field, the anomalies induce. Of course, you always have the usual ohmic conductivity, because this is just a system of electrons, and the electrons always are conducting. It's an ungapped system of electrons. But what this tells you is that you get an additional channel for transport, charge transport, and heat transport due to the anomalies. And in particular, at low magnetic field, it has this increasing. It increases the conductivity proportional to b squared. So that's and this is now taken, or it's taken as one of the standard signatures for the realization of this anomaly physics in this Weyl semi-metal. So the first convincing, I think, experimental paper which showed this is by Zhang Li, Dima, and collaborators, where they showed, so the red dots are the measurement, the blue dots is the theoretical curve, and that shows this very nice quadratic behavior, except for this cusp in the middle. And this is still, to me at least, this is, I don't know if this has been resolved, this is still somewhat mysterious where this cusp comes from. It's not from this naive semi-classical or quantum anomaly-induced transport. This is not predicted. It's also, it doesn't seem to be universal. In every material, the cusp is bigger or smaller, and it's not even universal if you ask knowledgeable people of what's the origin, because some people say it's a well-known phenomenon which is called weak anti-localization, which probably you all know. Other people say no, they have calculated it, and it's weak anti-localization because it's very weak, and this effect is much bigger than this weak anti-localization, so it's something else. Some people claim it's a surface effect because these probes are not very big. So to my knowledge, this is still not completely understood where this comes from. But if you go to a little bit higher magnetic fields, then you're still in this nice quadratic regime. The same you can do with so this is if you just have a magnetic field and measure electric conductivity sourced by potential, electric potential. You can also take the driving force to be a gradient in temperature. And here I had the honor to collaborate with the experimental group at that time in Zurich, led by Johannes Voth. And again, you see this typical quadratic enhancement for small magnetic field. This cusp is much less prominent for this material. This is niobium phosphide. This is zirconium pentatelluride. And then this thing switches off at larger magnetic fields. And that is also something which you easily predict from the theory, because back in the theory, it tells you for a large magnetic field, precisely the current which is sourced by the temperature gradient, a large magnetic field switches off. So this conductivity goes to zero. And so you see less and less effect for larger magnetic field. And then finally, this is, here again, you have this cusp behavior. I guess this and this, I guess the curves are upside down, but this measures thermal conductivity in, I guess this is the material which I don't even dare to try to pronounce, for different temperatures, and here's the magnetic field strength. And again, you see this typical quadratic behavior, and then linear, because this is a very strong magnetic field and dominated by lowest Landau level physics in the quantum limit. And they also showed experimentally that this satisfies the Wiedemann-Franz law, which is also, as I emphasized, an outcome from these anomaly coefficients. Okay, now I am pretty much, I think, out of time, so I will probably leave some time for questions and finish here. So I think one of the basic lessons from quantum field theory is that while fermions, chiral fermions, have these anomalies, the usual axial anomaly and also these gravitational anomalies, what we have learned is that while usually the anomaly is expressed as a non-conservation of the current in background fields, like electromagnetic fields, or in curvature, there are effects where you substitute the fields by state parameters like temperature and chemical potential, and you generate currents. It leads to something which I call anomalous transport theory, which I think is useful. You can very easily, explain phenomena which can be measured on grounds of symmetry principles plus quantum anomalies. The theory seems to be, so far as I can see, compatible with what the experiments see. And I think it's necessary for the materials to show this phenomena, because if you want to call something a Weyl semi-metal, it should really show the physics of these anomalies. So it's really good evidence that indeed these are materials in which the quasi-particles are described by something like a Weyl equation or by Dirac equation in certain background fields at finite temperature, at chemical potential. There are, of course, many other applications of this. I've concentrated here to the applications in condensed matter, but there is a very active field. There are hundreds, if not thousands, of people working on large experiments, colliders in the US, at the relativistic heavy ion collider, searching for signatures of these effects in the quark-gluon plasma. It might lead to generation of magnetic fields in the early universe and many other things. You might think about possible technological applications. So what I have not emphasized so much, which I should have done, is that these are actually dissipationless currents. So they don't care about these small scattering events, right? So the small momentum destroying small scattering within a Weyl cone, the anomaly doesn't care about it. So if you have such an anomaly-induced flow, you can put some obstacle into this flow and it just goes around and doesn't care about this obstacle. So it's something like dissipationless, and you can wonder if you can use this for some electronics or even for quantum computing or some other technological application. Okay, thanks. That's all I have to say about so far.
Okay, well, we thank very much, Karl, for your interesting talk, and we open to some questions. If somebody has something to ask, please proceed. Are there any questions then from the audience? Just
yeah, I have a question.
Go ahead.
Hi, Anna. Hi.
Hi, Karl. Thank you for the talk. In the beginning of your talk, when you expressed the anomaly in terms of these coefficients D, A, B, C,
yeah.
So your condition for the anomaly manifest itself in a rotating system is that these coefficients, the sum of them are different from zero.
Yeah. So, for example, for this effect here.
Yeah. This is totally equivalent to have a mu5.
Yeah. So a mu5 would be one of these guys here. Right. So you can think of this as being, for example, for a Dirac fermion, where you have left and right-handed symmetries, you can think of being axial and vector. And then that term would be activated by mu5. In fact, there's a term here which is just mu5 squared.
Okay. And then you have another term. So even if you don't have mu5, if you have temperature, you have this BA. Okay, this is another kind of mu5, right?
That's so. Where's the 5? The 5 would be here on this anomaly coefficient. What this tells you is that this A should be also a 5, so that would be an axial current. And what this tells you is that if you rotate the system of, say, Dirac fermions at finite temperature, you generate an axial current along the rotation axis whose strength goes like T squared.
Okay,
This term is only there for the axial current.
okay,
For the
this is
vector current, it's not there.
Chiral separation effect.
Yeah, that's a contribution to say the names are very complicated. Yeah, so that's a contribution to chiral separation effect, if you want. Yeah, that's a version of the chiral separation effect induced by rotation. Usually it's written with magnetic field, but you can also do it with rotation and just temperature. And you don't need any chemical potential or anything. Temperature alone does it. And you get this separation, chiral separation along the rotation axis.
Okay, okay, thank you.
Okay. Any more questions? Well, I have one. I mean, Karl, you have explained that the anomalies are basic for the calculation of this currents, transport current. But for example, in Weyl semimetals, you might have tilting and other properties of the Weyl semimetal, which you can understand as a violation of Lorentz symmetry from the field theory point of view. But the anomalies are not sensitive to these violations, so they don't see this this modification that should enter in the current properties of propagation or in the effective action. So do you think your method can work for this situation in which you admit Lorentz violating terms in the fermionic action?
Yeah, I think so. I think so. I think the method, this method will always work if you can describe the effective theory as some sort of a deformation of a Dirac action. Right? So, for example, here, this is already a Lorentz breaking term, right? Because this background, right, this already breaks the Lorentz.
Yes, with mu gamma 5, yes.
Exactly, yeah. So, and the formulas take this fully into account.
Yeah, but the other terms, for example, the tilting and the anisotropy, the chiral anomaly doesn't see this term. They do not enter in the chiral anomaly, which has the standard form epsilon FF. I mean,
exactly. So the point is, you can describe a tilt
yes,
by a sort of background geometry. Say a Vielbein. A Vielbein would do that, right?
Yes.
But it's, as far as I understand, it's not necessarily curved. It's still a flat space, but it's not, this Weyl cones are tilted. And then, for example, the usual anomaly, where do I have a good equation for that? You see, this form of the anomaly, that's actually independent of whatever metric the theory lives in, because this is can be written in form language, and it means it's a volume form by itself. You don't need a metric to define a volume element. You can just integrate it. So this anomaly is independent of any deformation of the system, which can be described by switching on some background gauge field, switching on some background geometry, some deformation of just being strictly Lorentz invariant. So of course, it's not Lorentz invariant because the electrons don't propagate with the speed of light. They propagate with the Fermi velocity, right? And all of this can be taken into account, can be written as parameters in the effective, sort of effective Dirac action, but none of these parameters would influence the anomalies.
Yes, but they should influence the currents, not the transport currents that you calculate.
Yes. But this presumably, I would think you can take that into account by how to. I think that can be taken into account by describing the system by a specific background metric. Then you have to think, what does the index mu mean in the formula? So I would then write the formulas for the anomaly and the anomaly induced currents in sort of a tangent space form. I don't know if this formalism is known, where you locally attach a flat space without any deformation, and then you can transform this result into the result which has the deformation, say the tilt of the Weyl cones or so, which you described by a Vielbein, and convert this tangent space into a world line index, and then these parameters would enter there.
Okay, well, yeah. Okay.
But the basic form of the equations, I think they are independent of any of this.
Okay, well, so thank you very much. I mean, are there any more questions? So,
I think there's not, Mauro?
If not, well, we thank. Yes, yes, go ahead.
Is there time for one more question?
Yes, yes, go ahead.
So regarding the anomaly coefficients, is this expression you wrote for the anomaly coefficients, the general expression, is that valid only at tree level, or how's the story? Because what's the role of higher order corrections? Because we know, for example, in QED that the axial anomaly does not receive higher order corrections and so on, but that will not be valid for any current.
Yeah, no, okay, so the anomalies, all the anomalies are subject to non-renormalization theorems. So none of these coefficients receive corrections. Now there is now. So that's the basic statement. That does not mean that these currents always don't suffer any correction. So one has to be careful. What can happen, and which has also caused some confusion, is when, I always said the gauge fields I have here, I consider to be classical fields without their own quantum dynamics. Under these circumstances, the currents do not get renormalized. The currents are what they are, and none of these equations do get renormalized. However, as soon as the gauge fields themselves are quantum objects, then you have this triangle diagram, and on one side of the triangle diagram, there come two gauge fields come out. If these are quantum objects, they can scatter amongst themselves, and give higher loop contributions to these expressions.
Okay,
But
yes,
the basic triangle anomaly diagram, it's this one which does not get renormalized. So the external legs which you attach to them, they can, and the vertices, they might get, but the basic anomaly triangle doesn't get renormalized. That's my understanding of what the non-renormalization theorem says.
Okay, I see, yes.
Okay, well,
thank you very much.
We don't have time for more questions, so we thank again Karl for the talk, and we proceed to the next one.